Meet our next speaker, Timon Ruban from Luminovo. He will talk about pragmatic hyperparameter tuning. Welcome.
Thank you. Should I use the microphone or? Yes, please. Yes? Is it better? Okay. Because it's a pretty small crowd, and that's actually, I like that, so maybe there will be more time for questions. Hi everyone, my name is Timon. I'm one of the co-founders of Luminovo, and I quickly want to talk with you guys about pragmatic hyperparameter tuning, which basically just means I'm going to tell you a little bit what I think about it, how I used to tune hyperparameters and how I do it today, or how we do it today at Luminovo. Maybe just quickly about myself. I was originally studied electrical engineering. My machine learning career, if you can call it that, started around 4 years ago when I did my master's degree at Stanford. I was very lucky from the timing to have people like Andre Karpathy over there, and I took all the machine learning courses I could. Back then, quickly worked at Google, did an internship in one of their deep learning teams, and then came back 2 years ago to Munich, and ever since kind of lead the AI efforts at Luminovo, where we do many different kinds of deep learning projects. But enough about me. Seeing that we're so few people actually right now, it still feels weird to talk into a microphone to 15 people. Please feel free to interrupt me anytime during the talk, seeing that there's only that few people. If you have a question that's interesting to you, that's kind of why I'm here, to talk about stuff that might help you guys out. Quick question up front, and then I'll just start and race through my slides. I actually have quite a lot of them, so I hope, I heard the speaker before was a little bit short. I might be a bit long, but I hope you guys won't mind. Who has trained a machine learning model before? The people sitting in the audience? Okay, most of you, that's good. Who's done anything fancier than a random search for hyperparameter tuning? Okay, 2, okay. Then depending on what you guys did, maybe you already know everything I'm going to tell you now. If not, also feel free to interrupt me. I'll say it one more time, interrupt me with questions. I'm really just here with the hope that after this talk you guys have learned something.
What did it, like you said you have masters from Stanford, like in what area was the master's in?
I was technically in the EE department, but I basically just did machine learning.
Ah, okay.
So I took all...
Engineering and...
Yeah, it's...
So I did something else. But
Okay, yeah. Yeah, I could tell you some fun stories about friends of mine that were also from Germany that studied EE before. I did CS at Stanford and ended up taking kind of fewer courses. They had to do requirements that I didn't have to do. So I really, was lucky enough to take all the machine learning classes there. Okay, let's start with hyperparameter tuning. So really quickly, here's the kind of a deep learning life cycle, all the stuff you have to do usually if you want to get a deep learning model into production, from sourcing the data, labeling it, versioning it somehow, to deploying the models later on. And what we're kind of talking about, right, is this thing in the middle of we want to kind of find the right model architecture, we want to train it, we want to evaluate it, and then use that to find an even better architecture and train the model even better. And maybe quickly up front, so I know this talk is about hyperparameter tuning, but in my experience, maybe this is one of the main takeaways you should take from this talk about hyperparameter tuning. It's actually, in real-world projects, very unimportant in some sense. So usually these two questions, I quickly want to put them up here so that we get our priorities straight, are usually much more important. So there's about how you split your data and how you evaluate your models. There's a lot of things you have to think about to properly answer those questions, and that's usually much more important than hyperparameter tuning. That being said, the rest of this talk is about hyperparameter tuning, and it's an interesting problem in itself. And I guess this is the only stuff I'll be talking about. So what do I talk about when I talk about hyperparameter tuning? I quickly try to put a definition up on the slide that yes, maybe every self-trained economist in here can appreciate. So hyperparameter tuning is really just about making efficient use of your available scarce resources to find the best possible model for a given data set and evaluation metric. And you can already see for given data set and evaluation metric, so we're kind of assuming that we've already answered these two questions, and now it's really just about, given what we have, how can we find the best model. And the other important part is the scarce resources. So what do I mean when I talk about that? Okay, I think my emojis did not make it into the PDF export from the Google Slides. So I will have to improvise a little bit. I think here I had a like emoji that was like a money bag and a clock. So what I meant is the scarce resources we usually talk about are time. That's one kind of developer time, and the other one is computing resources. So like GPUs or something, or how much you have. And in the end, kind of both of them boil down to money, right? So if you're talking about AWS or cloud computing stuff, there it's kind of the same thing, how much money you have and how much computing resources you could throw at a problem. And so usually in the real world, you're always working in a very constrained setting. So that's how it is for us usually. We have like a week maybe now, or like a certain amount of budget on AWS that we can spend to kind of solve this problem, but no more. And so we want to make sure we can do the best job that we can do with those scarce resources at hand. Seeing this, there's a kind of 3 paths usually you can throw yourself onto if you want to get better machine learning models. One is to wait for better hardware, one is making more efficient use of existing hardware, and the other one is finding better a priori insights. And again, what we're focusing on now is kind of the one in the middle, even though if you look back, I guess what these guys did when they first came up with these algorithms is that they just chose option 1 to wait for a little bit better hardware. But yes, we're focusing on making more efficient use of existing hardware. And so what I quickly want to do, I want to give you a quick kind of overview of how hyperparameter tuning is often done today, how I kind of used to do it, how my own machine learning journey started, and then we'll do a deep dive actually on quite a few algorithms, but they're all very simple, and that's why I hope I can race through them with you, because they're all very intuitive. We'll talk about population-based training, which is an algorithm published by DeepMind 2 years ago. We'll talk a little bit about Hyperband, and then about Bayesian optimization and how you can combine the two to do good automated hyperparameter tuning. But if we start with the basics, before going to automated hyperparameter tuning, there's kind of 2 ways of how you can do hyperparameter tuning, and one of them is you can do it in parallel or sequential. And so kind of all the methods we'll be talking about kind of are either parallel or sequential, or, and this is kind of the clue when I started hyperparameter tuning, you can try to do both. So what I mean by that is that when I first started hyperparameter tuning, during my time at Google, during all my classes I had at Stanford, it kind of looked like this. I usually had a few machines up and running where I would start a random search in parallel, and then after a while I would like SSH onto my cluster again, and I would look at the tensor board or something like this and see which of the experiments crashed, which ones performed really well, which ones didn't, and then shut down all the ones that didn't work well or crashed because the gradient exploded, and continue with only the ones that were good, and then start a few new ones maybe if I had available computing resources again. And so this is kind of a combination of, in some sense, parallel and sequential search, with the big drawback that the sequential part of this search was being done by me in kind of a manual fashion. And so back then I was very motivated to do lots of hyperparameter tuning, and I really enjoyed always looking at my experiments and how they were doing and kind of babysitting them to the very end to make sure I would get a good model for whichever project I kind of had at hand. But of course, that's not really how you want to do hyperparameter tuning. Ideally, you would spend even less time on it, that you can spend even more time thinking about these 2 other questions, or that I talked about in the beginning, of how to split your data, how to evaluate it, and maybe even what to try instead of just hyperparameter tuning. And so the next logical step would be to think about how we can automate kind of this process that already works pretty well actually. So generally, and this is maybe one other takeaway, if you don't have time to implement any kind of automated hyperparameter tuning, random search is pretty good. And we will see in a few comparison charts I showed to you later is that many of the like naive automated hyperparameter tuning approaches are actually not much better than random search, depending on what you look at. So yeah, I guess next takeaway, next to don't spend that much time on hyperparameter tuning. If you don't have enough time to once set up a good automated hyperparameter tuning pipeline, random search is also fine. But assuming that you do machine learning projects a lot, you should try to automate them. And maybe if you guys have heard these buzzwords of AutoML and all these things, and have never really kind of had the time to really dive deep what it means, maybe to take away a little bit of the fear. And some say it's automating. What we're doing here is really, really easy. You can really just do a random search, and the only other ingredient that you need to automate your hyperparameter tuning is what I call the one metric rule. This is a rule we have at Luminovo, is that for any machine learning project that we do, we want to choose one metric that we agree on beforehand, that we try to optimize, and that we can then use to compare the different models and which one's best. And this is actually usually a pretty difficult question. Often there's many different real-world constraints that you try to fulfill. Sometimes you don't really know, is this more important, or this, or this, or this? And you can try to reflect these trade-offs in your metrics, but kind of agreeing on one single one is pretty hard. But once you've done it, then AutoML is really easy, because you could just do a random search. You could, right, instead of babysitting, what I used to do back then, if I had lots of resources, I could just start a big random search over my hyperparameter sets, add the one metric rule, which basically then at the end will just pop up the best model according to my one metric, and bam, I have automated the process that I want to do. And this is kind of the easiest way, and that's also fine. And every now and then we'll have projects, or in the beginning at Luminovo, this is kind of how we used to do things. But seeing that our G-Cloud credits that we get for free are limited, and we want to make the best use of it, we then started thinking about how can we make even more efficient use of the scarce resources we have to find the best models that we can. And these are all the different algorithms I want to talk about with you now. When it comes to AutoML, or automated hyperparameter tuning, I talked about parallel and sequential before. Another way to kind of divide this up into groups is model-free and model-based. And for whom these words are too complicated, the ideas are actually really simple. So all model-free algorithms for hyperparameter tuning, for deep learning especially, are based on the very simple notion that you can stop an experiment when it's bad. So if you run stochastic gradient descent for a CNN or something, right, it runs over time, and you can just, if the gradients explode, or if it's bad, or the other thing is better, then it's really easy. You can just stop it and start something else. And that's basically what I was doing by hand back in the day. And so PBT, the population-based training, and Hyperband, the two things we'll look at in a second, are based on the super simple idea that, well, you know what, let me just stop the evaluation of a hyperparameter configuration that is bad. Whereas the other kind of hyperparameter tuning that you can do, that's usually model-based, such as Bayesian optimization that you might have heard of. And if you don't know what it is, we'll quickly do a summary of it, because the idea, again, is very, very simple. It's based on this idea, hey, you know what, I would, instead of just stopping the ones that are bad, I'd prefer to not even evaluate the bad configurations in the first place. And that's really basically the only idea behind Bayesian optimization, is to use a model that kind of models which one you might think are bad and good hyperparameter configurations, and then choosing the good ones. Okay, any questions so far? I kind of raced through all of these slides because I wanted to make sure we have enough time to really answer questions, if there are any, about the different algorithms that we go through now. The one metric rule? Yeah, absolutely. So this comes actually from my time when I was a research assistant in Andrew Ng's lab, and there or also during taking the class there, he always told us, hey, it's a really good idea to have this one metric, to agree on it beforehand. The reason is the following, that you usually, what if you don't adhere to the one metric rule? So let's say you're doing a classification problem, and you think, here's all these metrics that I find interesting. I want to know about the accuracy, I want to know the ROC, AUC, I want to see a precision recall curve, and there's all these different things you might want to look at. And usually it's a good idea to do it, But if you don't agree on one metric beforehand, so I guess this rule is only really important if you are working in a team, A, or B, want to do automated hyperparameter tuning. At some point, once you've trained multiple models, you'll have to decide which one are you going to use, which one's the best one. And let's say you have two metrics and you didn't decide beforehand how to make the trade-off between them. Well, you're going to have to do it later, because then you might have a model that's better, it's better accuracy, but a worse ROC, AUC. And then what are you going to do? And usually there's an answer to this. So it's usually based on the problem that you're trying to solve of what is kind of the trade-off you want to make. And yeah, one kind of really important rule that I think has helped us a lot at Luminovo is to not ever start training any machine learning models usually before we at least have a best guess for what our one metric will be now. We sometimes change it later as we understand the problem better, but at any given time you should have one metric, because then it also makes it really easy to kind of parallelize your machine learning experimentation. If you have, let's say, a team of 4 engineers that are all trying to solve this one really, really important machine learning problem, I guess it needs to be pretty important if you want to pay 4 people to work on it, because machine learning engineers are pretty expensive. And then they can kind of just go off by themselves, go into their hole and come back and then compare their one metrics against each other. And there's something like oddly motivating to, I guess, numbers-driven people like me of having this one number that you always watch increase a little bit. And if you've increased it by a little bit more, then you're happy. And if you didn't, then you're unhappy. And I think for all those reasons, it's I think, a very good idea to kind of adhere to this one metric rule. Plus, the benefit is you can do AutoML, putting it more negatively. If you don't have a one metric rule, you can't do AutoML. Every single automated hyperparameter tuning algorithm relies on this, that you always need one metric to distinguish between what is good, what is bad. A process to choose the metric. I wouldn't say a process. There's always kind of the same things that you need to think about usually, but then there's a lot of problem-specific context. Maybe this should be my next talk, how to choose the one metric with 10 examples on how to do it. But a good question. Thank you. Any other questions so far? Maybe quick show of hands. Who here already knows what Hyperband is? Who already knows what population-based training is? And who already knows about Bayesian optimization? A little bit, okay. So then good that we're doing this talk together. Maybe I can teach you a thing or two, but feel free, again, as I said 5 times before, to interrupt me if something is unclear or if I race too fast again. I've thought about this stuff a lot, and it's possible that I skip a detail or two that's important for your understanding, and if I do, please stop me. Okay, let's start with population-based training. I'll start with it because this was kind of my favorite and first love when it comes to automated hyperparameter tuning, because I kind of raced to it before, but you've seen this picture before when I talked about real-world hyperparameter tuning, what I used to do when I used to spin up a bunch of machines and then manually watch once things crash to then start new sets. Or if all of them crash, what you'd often do is you start with some range of a learning rate, for example, and then you see, it's too big, and all the big ones, my gradients explode, so I'll change the range in which I search a little bit, and then keep looking in that more narrow range in my random search. And this kind of intuition, that's exactly what population-based training does, and I think that's why I liked it a lot, and why we started using it at Luminovo for the longest time. To automatically tune hyperparameters. Let's quickly go through it. This picture is all we need to explain it to you, I hope, at least, because the idea behind it is very simple. So you usually start with a random search. So in this case, we have a population of 2, I guess, in this image, where we have, let's say we have 2 different machines with a GPU each. So on each one, we can train our neural network that we want to optimize. Each one starts out with a different set of hyperparameters that we choose randomly. And then the thing that population-based training does is basically automating exactly the manual step I did before. That every now and then, so that's, for example, every epoch, it will check in, look at the performance of the model we're doing. So usually in the case of a deep learning neural network, you'd probably look at your one metric on the validation data set. And then you would check, okay, of all the models I'm running right now, which ones are the good ones and which ones are the bad ones. And the idea is to do an explore step, where exploit means, you know what, let me stop all the bad ones. So it could be something like the lower quantile or the lower half of trials that performed worse. I'll stop them and I'll exploit the other trials by copy-pasting over my model weights and my hyperparameter configurations I had from the good trials. Because here I've already had a model that's been trained for an epoch and it's done pretty well, so I don't want to start at 0 again. I would like to continue training with the good model I've had. That's the exploit step. But if I only exploit, then I'd have now 2 models that have the same weights and the same hyperparameters and would just train in the same way, except for some stochasticity you might have in some of the GPU operations. And so that's why you need an explore step. And the explore step is really simple. It's usually just, you know what, let me wiggle my hyperparameters a little bit. Or in some cases, completely resample. So I think for the learning rate, that's maybe the most intuitive hyperparameter to understand population-based training. Let's say the learning rate is the only thing we're tuning. So we'll start with a bunch of models with different learning rates. After one epoch, we'll check, hey, which one was the best learning rate? Which one was the best model? Then we'll take that model, take the weights. We'll wiggle the learning rate a little bit again, so we'll maybe multiply it by 1.2 or 0.8, like make it a little bit bigger or smaller, and then keep training with that. And that's it. And then you do this repeatedly. So every now and then, for example, every epoch, you check in, you stop the bad trials, and you continue with the good ones. And so in some sense, and that's why I really liked it, it's very simple, it's very effective, and so there's a paper by DeepMind, by the way, I think I said it before. There's a very good blog post also with some more visual things that I didn't put in the slides because there's a bunch of other algorithms I want to talk to you about. But they basically showed back then, this was 2017, for a bunch of reinforcement learning problems. These are the first 3, but then also a GAN and for machine translation, that they could just take back then state-of-the-art kind of models, just run it again, the exact same thing with PBT, and they could kind of, in an automated fashion, improve on the results they had before. Because if you really care about kind of small performance improvements, hyperparameter tuning is very important in machine learning. I guess this is how it differs a little bit in the real world and academia, is that in academia small performance improvements are often very important. For most of our projects, usually it doesn't matter. We of course want to get the best models, but there's much bigger risk factors usually that can crash your entire project than just choosing the wrong hyperparameter tuning. But so this is cool, and it works, and we've used it a lot actually at Luminovo, and it's kind of a very reliable way to, without having to think a lot, kind of just pressing the button and getting a very good model spewed out at the end of your automated hyperparameter tuning pipeline. So if we quickly look at the things, so we have fewer wasted resources for doomed trials. This is kind of what I was doing manually back then. I just didn't want to have my gradients explode and then machines running where the one crashed and there's basically an empty idle GPU that I'm not using at all. It's easy. So one of my favorite things about PBT is that you don't need learning rate schedules anymore. Because this is exactly what PBT can do for you, for these kind of dynamic parameters like a learning rate. It can find a schedule for you. The one problem with it, and that's actually why I'm not stopping the talk here, but continuing to tell you a little bit about the other automated hyperparameter tuning pipelines we use at Luminovo, is that it doesn't work for all hyperparameters. So let's say you want to have your model architecture, like if you want to use a ResNet or a DenseNet, for example, in a very simple case, they're both in Torch Vision, so I can quickly just throw them in an easy pipeline, and you want to check out which one's better. You can't really do that with PBT because, who knows why this won't work with PBT? Any ideas? So that's the first one. They might require different hyperparameters, but the other one is actually the exploit step won't work so easily, right? So I can't exploit a trained ResNet, copy paste it over into my DenseNet, because they have different architectures, and there's probably for certain model architectures there's heuristics that you could choose to potentially convert it, but for many it doesn't make sense. And so you can't really use this. Okay, so that's why the talk is not done. That's why we need to continue thinking about, ideally, right, I wouldn't want to think about anything. I just want to press the button, not worry about it, think about other stuff, and then come back and see what my best model is. And for this, there's another algorithm I want to talk with you guys about. The algorithm we actually use is called Hyperband, but it's based on an algorithm that's super simple. It's called the simple halving algorithm because it's so simple. It has simple in the name. And I'll quickly talk with you guys about that. And Hyperband just is a little bit more fancy version of the simple halving algorithm. But I think for our purposes, and there's other things I want to talk about, we can just look at this. So, does my GIF work? No! Okay, that's too bad. Maybe next time we should do the Google Docs version instead of the PDF. Then my explaining will need a little bit more time. It's still very simple. What we do in the simple halving algorithm is that you can start with a large set of hyperparameter configurations. Basically, we're again doing a random search. So in this case, we might have 25 different hyperparameter configurations that we want to try. What the simple halving algorithm or Hyperband does, it starts all of those 25 hyperparameter configurations and trains them for a certain amount of time. Let's say, again, an epoch for simplicity. And then after it's trained all these 25 things for one epoch, it will have a look and it will say again, okay, hey, which of these were good and which ones were bad? And then it will kill all the bad ones and keep the good ones. Sound familiar? Because it's kind of the same idea as before. But this one is even simpler than population-based training because we're not doing an exploit-explore step. We're really just killing the bad ones. So this GIF, the way it looked, I'm really sorry you can't see it, is that it's just first you train these for this, and then I kill all the bad ones, and I just keep training with the rest. And the one and last idea, and then you have basically understood Hyperband, is that for the next iteration, I now train all my models twice as long. So now for the next, basically my better half, I'll now train them 2 epochs. So after the second iteration of simple halving algorithm, each of them will have trained for 3 epochs. And then after that, I'll train it for another 4, where it's 7, and then for another 8. And the idea of it really is just the same that I said before. It's kind of the idea of most of these algorithms that are model free, that I want to kill bad. I want to use most of my computing resources on the good trials and not waste them on the bad ones. Say that again?
You mean that the final candidate you automatically pick in the first set that you...
Yes, exactly. So this is how it's different to PBT actually, and that's why we don't use Hyperband. We'll talk more about an even better version than this. But that's why we also use PBT sometimes, because here, and I have it I think on the next slide or something, we're back to learning rate schedules. So here, in some sense, what is your hyperparameter? There's no dynamic schedule that it will change over time. You have to set it kind of at the beginning. So here you need learning rate schedules again that you can parameterize and have your kind of hyperparameters be the ones you choose here. If you, How do you choose them? So for Hyperband, it's usually just a random search again. So for kind of, I guess, any of these algorithms we talk about, you define a search space for your hyperparameters that you want to kind of search in. If you want to have a really good model, you can make it really big, but then it'll take longer. No, you never have a guarantee. But it's kind of so, think about this, and I guess I think the next thing here, if you compare this to random search, it's really just strictly better than that. And so comparing it against that, actually, it's pretty good, especially in the beginning, because you don't have like with random search, you could kind of do the same, right? You're doing a big, try many things, and one of them will be good. And it's kind of what you're doing in Hyperband, but you kind of are better in the beginning because you kill the bad ones right away, and you just focus your resources. And the GIF you have here, that's why it starts with 10, is because usually the setting that you have is that the search space you want to try is much bigger than the machines you have. So here, this GIF was like, okay, you know what? We have 10 machines with 10 GPUs, but I want to try like way more things. And so I kind of after each other will try these different configurations. And yeah, and then so here's a comparison from a paper we'll talk about later that just compares random search with Hyperband. And as you can see, the cool thing about it is that in the beginning, it's much better because like it'll more quickly find good sets because it doesn't waste computing time on bad hyperparameter configurations. But in the end, if you let it run for a very long time, it's still kind of just in your initial set, just as the random search, and you're really not going to be much better in some sense than random search because, yeah, if you just run it for long enough, I guess that's true actually for everything that we talk about. If you have unlimited resources, well, random search is fine because it's gonna, if you make it the search space big enough, it might find the good hyperparameters that you want. Okay, and so for us as a startup actually, and I think I have it on one of the slides later on, there's two things, maybe I should have put them on the slides. There's a difference between anytime performance and final performance that's very important to a startup like us. So what I mean by anytime performance is that you want to think for your hyperparameter tuning algorithm that you use, is that at any given time, so no matter if I kill this like tomorrow or in a week, I'd like to have good performance. I'd like to have a good model. And this is actually usually more important to us than final performance because we usually work within very limited kind of sets. We usually don't care so much if it's like 0.1% better or worse. We just kind of want to quickly find the more or less best model for the problem that we're trying to do. And that's why something like Hyperband is actually great because we probably won't run it for like that long, but we very quickly want to have already a good configuration that we can find. And the other performance that would be nice to have, and that's the next thing we'll talk about, is just having good final performance, of course. In some sense, of course, it would be cool if the last model I get, if I do train it for a long time, is also kind of the best one I can find within like a reasonable time. And so Hyperband, I put it in the top, has really good anytime performance because it's like it'll always quickly find good models, even though it might not find ones that are much better than random search in this case. Okay, and so the cool thing, if you compare it to PBT, is it has the same idea of fewer wasted resources for doomed trials. It does work for all hyperparameters, right? So you can, whatever you mean by hyperparameter can be whatever. But we kind of lose this property of having adaptive hyperparameter schedules. So we still need learning rate schedules, for example. Okay, any questions so far? If not, we're going to go one step cooler, and then you've really raced through basically half of the hyperparameter tuning world and literature in just 30 minutes, so you can be proud of yourself if you make it to the end of the talk. We'll quickly talk about Bayesian optimization. If you remember one of the earlier slides I had, Bayesian optimization is a sequential method, usually, right, that tries to avoid evaluating bad configurations in the first place. And so the way it does that, this is an ugly slide, I'm sorry for it, but at least it's prettier than having a bunch of math up there, so I put it in words because the idea is still very simple. All Bayesian optimization methods usually fit some kind of surrogate model to approximate the objective function, so our one metric that we're trying to do well on, so objective function would be one metric on the validation set for most of the deep learning projects we do on, given all the prior hyperparameter configurations and their results. So basically, you're actually fitting another machine learning model, usually in Bayesian optimization. If I've run, let's say, and we'll come to this actually, how to combine it with Hyperband, but if you have run these 10 hyperparameter configurations, you have results for these 10, then you'll use that as your data set, with X being your hyperparameter configuration and Y being your one metric on the validation set that those things got. And given this little data set, you now fit another model that tries to predict which hyperparameter configurations will give you which results. And if you have a method like this, then, okay, what do you do? It's actually pretty easy. Well, you're gonna choose the next hyperparameter configuration given this model that you've just fitted. There's usually some exploitation trade-off that you wanna have in choosing these, so you might not always wanna exploit your model to choose what it says is the best one, but also do some exploration. And then you're going to evaluate that hyperparameter configuration next, and then you're going to repeat it. Now you have kind of 11 hyperparameter configuration that you've seen before, and you can use that model information again to fit a new model and choose the next one. And as you can see, it's kind of just a sequential, step-by-step. And it's actually very simple, and also I didn't put the math up here, but also the math usually is not that complicated. It's just about which model do you choose to kind of approximate your objective function, and which is just a normal machine learning project again. The other one is, hey, how do you make this exploitation trade-off for choosing the next hyperparameter configuration? Okay, so the cool thing about Bayesian optimization is that you can think about it, well, the more hyperparameter configurations I've seen, the better I can understand the search space I'm in, and the better I can be at picking the right or like the best or really good hyperparameter configuration. So it's a sequential method, right? I keep getting better and better because once I've run something, then I choose the next one, and in a sequential manner, I try this out. The bad thing about it is that in the beginning, it's not much better than random search. And it's kind of easy to imagine, right? If I don't have any data, then my machine learning is going to be shit. So the surrogate model I have is going to be shit. And so in the beginning, it's usually just as good as random search. And only after time, it's going to get better than just doing a simple random search. And so Bayesian optimization by itself is actually really shitty for, again, a startup like us, where usually we just care about getting more or less the best model, and then often random search does the trick, and you don't really need to use Bayesian optimization. And that's how, for example, how it was back in the day when I was at Google before they had their internal tool Vizier that I think now many people use there to tune hyperparameters, where my advisor back then also told me, I don't really mess with Bayesian optimization. Random search is probably going to be just as fine for your problem. But if you paid attention, I guess okay, let me not skip this. So we have good final performance here, but we have bad anytime performance. I guess this is the clue. It also works for all hyperparameters. And the other thing, that I forgot to mention, it cannot be easily scaled. And this is usually something we are also interested in. So whereas Hyperband, right, or the population-based training, I can run this stuff in parallel. It's a parallel search. I can say, well, this problem is really important, and my client needs the result by like Monday. So I'm going to start 100 machines and do a lot of this exploration in parallel. You can't really do this with the simple Bayesian optimization because it's sequential, right? I need to have the result of the first trial to pick the next one. And so that way it's going to be kind of slow. And if I really need the result by Monday, well, maybe I'm going to have to tell my client to wait 1 week longer. If you've paid attention or are still interested in what I'm saying up here, then it's probably pretty obvious of what you might want to try next. And this is actually the last algorithm I want to talk about, called BOHB. And it's really just Bayesian optimization plus hyperband. I think this is what it is. In the paper, they actually never define what they mean by BOHB, but it seems pretty obvious to me. And at least the explanation that I'm going to give you needs only this slide because it's super easy. And the idea of BOHB is, I think, super trivial. I think, I have no other slides other than showing how cool it is in the results. Because, think about how could you combine this. It's actually really easy. If I had the GIF, I would show it, but we don't have it, so I'll say it in words. If we run Hyperband, and let's say again we have the setting that we have 10 machines where we can evaluate 10 configurations in parallel, but I really have this huge search space of 1,000 configuration settings I would like to have a look at, but I can only have a look at them 10 at a time. Well, then you could think what Hyperband does by default is just pick the next configuration always randomly. So it'll run the first 10, then it'll pick a new 10 random ones, run those 10, and usually run through it until it can promote one of the trials to the next rung, where it runs it twice as long as before. And it's pretty obvious, and this is really all that Bob does, is that instead of picking randomly the things, you might want to use the information you've already gathered about the hyperparameter configurations you've used so far to build a model and to use Bayesian optimization to pick the next ones, not in a random fashion, but kind of in a best guess fashion where you use Bayesian optimization to pick the next hyperparameter configuration. And that's really all there is. There's a few details about how they do it exactly, and Bob is in that. One thing that's more complicated than normal Bayesian optimization is that you want to fit a surrogate model for every budget that you have. So budget was for all the configurations you run for one epoch. You're going to use all those results to fit one model, and then you're going to use another model for all configurations you've run for 3 epochs, so 1 plus 2. And for each one, you kind of do this in between, and you're always going to try to use the model that has the most information, because the longer these things run, the more information you will have about which hyperparameter setting is actually better or worse. But other than that, it's really exactly what this slide says, and that's why I decided to not put any other. It's just Bayesian optimization plus hyperband. And the cool thing about it is, and I think this is almost my last slide, and then I'll open it up to questions, that is kind of combines the best of both worlds, right? So it has the big speed up and the good anytime performance that we expect from hyperband in the beginning, right? Because we'll quickly shut down the trials that are bad and only continue with the ones that are good. But it also exhibits this nice, good final performance that Bayesian optimization has, that we kind of leverage, that we've seen a lot of configurations over time to pick better and better ones. And so I guess I have another takeaway on the last slide, and I've mentioned it multiple times before, but for us at Luminovo, these are kind of the 2 things we use today. PBT, if we want to find schedules for hyperparameters, and BOHB kind of for all the rest, where we just want to press the button and not think about it. And this is my last slide. Maybe the maybe even more important takeaway is that if you do regular machine learning projects, hyperparameter tuning is not what you should be spending your time on. And so you should set it up in an automated fashion, so that not because you should spend more time on hyperparameter tuning and thinking about automated, just because it's automated and you don't have to think about it anymore. And that's how kind of most projects are for us today, that we kind of don't expect anyone to set up a new machine learning pipeline with hyperparameter tuning or something, but we want the people to think about the problems, to think about the value propositions that these machine learning models bring when deployed at the client. We want our people to think about the data, about which one metric to choose, and kind of all the difficult stuff that we're paying people to use their brain, and not hyperparameter tuning. And so, maybe this was the weirdest talk you guys have heard about hyperparameter tuning, that started with hyperparameter tuning is unimportant and ended with hyperparameter tuning is unimportant. But really do think so. That being said, it's pretty fun to read these papers and to think a little bit better about how you can make the most efficient use of the scarce resources you have when you try to find your best model. Thank you very much.
Many thanks to all of you for sharing this day with us. This year's Munich AI Summit was devoted to the role of women in AI. Looking forward to Munich AI Summit 2020. See you next year.